In 1981, astronomers mapping galaxies in the constellation Boötes found a hole in the universe. Not a gap between two clusters, not a thin spot in the cosmic web. A sphere of almost perfect emptiness 330 million light-years across, containing roughly 60 galaxies where 2,000 should exist. Standard simulations of how the universe builds structure struggle to produce anything this barren at this scale. The Boötes Void sits in our maps like a wound in the architecture of reality, so large and so empty that cosmologists still cannot fully explain how it formed. One astronomer calculated that if the Milky Way sat at its centre, humanity would not have discovered other galaxies until the 1960s. This is not a story about nothing. This is a story about how nothing became a problem. If you enjoy deep journeys into the biggest questions about our universe, go ahead and hit that like button and subscribe. It really does help more than you might think, and I genuinely appreciate every single one of you who sticks around for these explorations. Now, with that all said, get yourself comfortable. Let's begin. Look up at the night sky on a clear evening, and you will see thousands of stars scattered across the darkness. Every point of light belongs to our galaxy. Every constellation you can name is a local landmark within a single spiral of roughly 400 billion suns. The view is rich and crowded and full of implied structure. It suggests a universe packed with matter, a cosmos where brightness is the default condition and emptiness is merely the quiet space between interesting things. That suggestion is one of the most misleading impressions nature has ever produced. The universe is not full. It is overwhelmingly, staggeringly, almost incomprehensibly hollow. The galaxies you see, the clusters astronomers map, the filaments and walls and superclusters that define the largest structures in existence, all of that matter crowds into less than 20% of the total volume of observable space. The remaining 80% is void, not small gaps between neighbouring galaxies, not modest pockets of thinness between clusters. Enormous spherical regions stretching tens of millions, hundreds of millions, sometimes more than 300 million light-years across, containing almost nothing. A few lonely dwarf galaxies drifting through darkness so complete that the nearest bright neighbour might lie further away than the distance from Earth to the most remote quasar visible in a backyard telescope. If you could somehow place yourself at the centre of one of these regions and look outward in every direction, you would see nothing. No galaxies, no clusters, no glowing nebulae, no filaments threading through the distance, just blackness stretching to a horizon so remote that light from the nearest significant structure would need tens of millions of years to reach you. The isolation would be almost beyond comprehension. These regions are called cosmic voids. They are not truly empty in the strictest sense. They still contain trace amounts of dark matter, wisps of hydrogen gas, and the occasional small galaxy that managed to form despite the impoverished environment. But their matter density is so dramatically lower than the cosmic average, often only 10 to 20% of the mean density of the universe, that for all practical purposes they represent the closest thing to absolute emptiness that the cosmos produces on large scales. Cosmic voids are the dominant feature of the universe by volume. They are the rule, not the exception, and they are not accidents or mysteries in themselves. They are exactly what the physics of structure formation predicts should exist. Voids are the natural, inevitable consequence of gravity doing its work over 13.8 billion years of cosmic evolution. Every void you could find in the observable universe traces its ancestry back to the first fraction of a second after the Big Bang, when quantum fluctuations created the tiniest ripples in the density of matter and energy. Those ripples determined everything that followed. They are the reason galaxies exist. They are the reason filaments formed. And they are the reason that most of the universe is dark, silent, and profoundly barren. Understanding what a void is requires understanding the structure it lives inside. And that structure is far stranger than any arrangement humans encounter in daily life. The universe on its largest scales does not resemble a uniform ocean of galaxies spread evenly across space. It resembles foam. Imagine the inside of a sponge, or the lattice of soap bubbles clinging together after a bath. Dense walls and filaments of matter form an interconnected web, and between those walls lie enormous hollow bubbles. This architecture is called the cosmic web, and it is the single largest coherent structure in nature. Nothing else comes close. No galaxy, no supercluster, no wall of galaxies approaches the scale of the web itself. It spans the entire observable universe, and almost certainly extends far beyond it. Galaxy clusters, the most massive gravitationally bound objects in existence, concentrate at the nodes where multiple filaments intersect. These nodes are the busiest intersections in the cosmos, the places where gravity has pulled the most matter together over the longest periods of time. Thousands of galaxies packed together in these clusters, surrounded by superheated gas radiating in X-ray wavelengths and embedded in halos of invisible dark matter that outweigh the visible galaxies by factors of 10 to 1. The Virgo cluster, the nearest major cluster to our own galaxy, contains more than 1,300 galaxies and sits roughly 54 million light-years away. The Coma cluster, farther out at about 320 million light-years, is even richer and denser. These clusters mark the densest concentrations of matter in the cosmic web, the places where the universe is at its most crowded, its most violent, its most active. Stretching between these nodes run filaments, long, sinuous chains of galaxy groups that can extend for hundreds of millions of light-years. These cosmic threads channel matter between clusters like rivers feeding into lakes, connecting distant nodes of the web across staggering distances. Filaments also organize into walls, vast sheet-like arrangements where galaxies gather in concentrations above the cosmic average. The Sloan Great Wall, one of the largest known structures of this kind, stretches roughly 1.4 billion light-years in length. Together, the nodes, filaments, and walls make up the scaffolding of the universe. They contain most of the mass. They host most of the star formation. They are where galaxies interact, merge, and evolve through the violent gravitational encounters that shape their structure over billions of years. All of the dramatic cosmic events that fill astronomy textbooks, colliding galaxies, starburst regions, active galactic nuclei, growing supermassive black holes, all of them happen almost exclusively in the dense parts of the web. Between the filaments and walls lie the voids. They take up most of the room while containing almost none of the mass. If you could somehow stand outside the observable universe and look at it from a great distance, the bright parts, the galaxies and clusters and filaments, would appear as a thin, glowing web, delicate and sparse. The dark parts, the voids, would dominate everything. You would see a universe that is mostly darkness, punctuated by occasional fragile threads of light. You would not describe it as full. You would describe it as empty with structure around the edges. This cosmic web was not immediately obvious to astronomers. For most of the 20th century, the three-dimensional arrangement of galaxies remained hidden. Telescopes could photograph the sky and record the positions of galaxies projected against the celestial sphere, but measuring their true distances was enormously difficult. Two galaxies that appeared side by side in a photograph might actually be separated by billions of light-years, with one sitting far behind the other along the same line of sight. Without accurate distances, the cosmic web could not reveal itself. Astronomers knew galaxies existed. They could count them, classify them, study their light. But the grand architecture connecting them, the vast web of filaments and the enormous voids between them, remained invisible for decades. The breakthrough came from redshift surveys. Starting in the late 1970s and accelerating through the 1980s, astronomers began systematically measuring the redshift of thousands of galaxies. Redshift quantifies how much the expansion of the universe has stretched a galaxy's light toward longer, redder wavelengths during its journey to Earth. The greater the redshift, the farther away the galaxy sits. By combining a galaxy's position on the sky with its redshift-derived distance, scientists could plot its true three-dimensional location in space. When they did this for thousands of galaxies simultaneously, the results were stunning. The universe had structure on scales nobody expected. Galaxies were not scattered randomly. They gathered into filaments and walls surrounding enormous empty regions. The first major void identifications came in the late 1970s when independent research teams found large, underdense regions in their galaxy maps. The pioneering CFA redshift survey, led by Margaret Geller and John Huchra in the 1980s, produced some of the first clear visual evidence of the cosmic web, revealing a distribution of galaxies that looked unmistakably like the surface of a foam. Their famous slice of the universe diagram showed galaxies concentrated along thin walls and filaments surrounding dark, empty voids. The pattern was dramatic and obvious. It was the first time anyone had seen the cosmic web laid bare in observational data. More surveys followed through the 1990s, each one mapping deeper into space and revealing an increasingly intricate web. The 2-degree field galaxy redshift survey measured redshifts for over 200,000 galaxies. The Sloan Digital Sky Survey, which began observations in 2000, created some of the most spectacular three-dimensional maps ever produced, spanning billions of light-years and resolving the cosmic web in breathtaking detail. Filaments twisted and branched like blood vessels. Voids appeared as dark bubbles, sometimes hundreds of millions of light-years across. The architecture was unmistakable and undeniable. The universe was organized on scales that no one had predicted even a decade earlier. These maps confirmed a picture that theorists had already begun to develop. The cosmic web is not a random arrangement. It is the direct product of gravity, amplifying tiny initial density differences over cosmic time. And the story of how that happens reaches back to the very beginning of cosmic history. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. During this brief epoch, lasting perhaps 10 to the negative 35 seconds, the universe expanded by a factor so enormous that regions smaller than a proton were stretched to sizes larger than the observable universe today. This expansion did something remarkable to quantum mechanics. At quantum scales, particles and fields fluctuate constantly. Energy appears and disappears. Density varies from point to point in ways dictated by the uncertainty principle. Normally, these fluctuations are confined to subatomic scales and average out over any macroscopic distance. But inflation stretched them. It took fluctuations that existed at the smallest conceivable scales and expanded them to cosmic dimensions, freezing them into the fabric of space-time. When inflation ended, the universe was left with a nearly uniform distribution of matter and energy, but not perfectly uniform. Tiny density variations remained, imprinted across all scales like a watermark pressed into the structure of reality itself. Some regions were a fraction denser than average, others were a fraction less dense. The differences were minuscule, roughly 1 part in 100,000, but they were enough. After inflation, the universe continued to expand, but now at a much slower rate. Gravity began its long, patient work. Regions that started slightly denser than average exerted slightly more gravitational pull on their surroundings. They attracted matter from neighboring regions, growing denser still. This created a positive feedback loop. The denser a region became, the stronger its gravity grew, the more matter it attracted, the denser it got. Over hundreds of millions of years, these overdense regions collapsed into the first stars, then into galaxies, then into clusters of galaxies, then into the filaments and walls of the cosmic web. Meanwhile, the opposite process occurred in the underdense regions. Regions that started with slightly less matter than average lost mass to their denser neighbours. As matter drained away toward the growing overdensities, the underdense regions became even emptier. They expanded faster than the surrounding denser space, thinned out further, and gradually evolved into the voids we observe today. This process is called gravitational instability, and it is one of the most thoroughly tested and confirmed mechanisms in all of cosmology. It turned barely perceptible initial ripples into the grand architecture of the cosmos. Every galaxy, every cluster, every filament, every void is a direct descendant of quantum fluctuations that occurred before atoms existed. The universe built itself from noise. And the beautiful thing about this process is that it is entirely determined by the initial conditions and the laws of physics. Given the right starting density fluctuations and the right combination of gravity, dark matter, and dark energy, the cosmic web builds itself automatically. No fine-tuning required. No special ingredients needed, just gravity and time and the slightest imperfections in what was otherwise an almost perfectly uniform beginning. The evidence for this picture is overwhelming. The cosmic microwave background radiation, the faint afterglow of the Big Bang, provides a snapshot of the universe when it was only 380,000 years old. At that moment, the density variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree from one direction to another. Warmer spots corresponded to slightly higher density. Cooler spots corresponded to slightly lower density. Satellites, including the Cosmic Background Explorer in the early 1990s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck spacecraft, launched in 2009, have mapped these temperature variations in exquisite detail across the entire sky. The maps reveal a mottled pattern of hot and cold spots at various angular scales, encoding the initial conditions that determined all future structure formation. Scientists can take this map and feed it into computer simulations that model the physics of gravitational collapse, dark matter clustering, gas dynamics, and dark energy over 13 billion years of cosmic evolution. The simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what galaxy surveys observe in the real universe. The match between prediction and observation is one of the great triumphs of modern physics. It confirms that we understand, at least in broad terms, how gravity shaped the universe from a nearly featureless beginning into the complex architecture we observe today. But that match comes with constraints. The simulations do not merely predict that voids should exist. They predict how big voids should be, how empty they should be, and how frequently voids of different sizes should appear in any given volume of the universe. This is a direct consequence of the initial conditions. The quantum fluctuations that seeded structure formation were random, but their statistical properties are well characterized by the power spectrum measured from the cosmic microwave background. Small fluctuations are common. Large fluctuations are rare. The probability of any given void forming depends on how large and how deep an initial underdensity it requires. Small voids, stretching a few tens of millions of light-years across, arise from common small fluctuations. They should appear frequently, and they do. Medium voids, extending 100 million light-years or more, require larger initial fluctuations. They are less common, but still expected and regularly observed. The standard model of cosmology, called Lambda-CDM, which combines Einstein's cosmological constant with cold dark matter, predicts a specific statistical distribution of void sizes. For the most part, observations match that distribution remarkably well. The trouble starts at the extremes. Lambda-CDM predicts that extremely large voids, those stretching several hundred million light-years across with severe density deficits, should be vanishingly rare. Not impossible in an absolute sense, just very unlikely. They sit at the far tail of the probability distribution, in the region where the numbers become small enough to create genuine tension between what we observe and what the model comfortably produces. A void that appears in only 1 out of every 1,000 simulated universe volumes is statistically unusual but perhaps tolerable. A void that appears in 1 out of every 10,000 is a significant outlier that raises eyebrows. A void that barely appears at all in even the largest cosmological simulations ever run is a problem that demands serious scientific attention. This matters because the void size distribution is not just a curiosity for specialists. It is a direct test of the initial conditions and the physics that govern structure formation across the universe. If the observed distribution of voids matches Lambda-CDM predictions across all sizes, the model passes one of its most important tests. If the largest voids are significantly bigger or emptier than the model predicts, something must be wrong, either with the initial conditions produced by inflation, with the gravitational physics governing collapse and expansion, with the properties of dark matter and how it clusters, or with the way dark energy interacts with structure on the largest scales. The voids themselves become diagnostic tools. They probe the foundations of cosmology through their absence of matter rather than its presence. To understand why voids grow the way they do, and why their growth has limits under standard physics, requires understanding the forces that control their interiors. Inside a cosmic void, the physics operates differently from the physics in a dense filament or a galaxy cluster. The most important difference involves the competition between gravity and dark energy. In dense regions, gravity is strong. Matter concentrations pull on their surroundings, resisting the expansion of space and holding structures together. Galaxy clusters are gravitationally bound objects. They stopped expanding with the universe billions of years ago and collapsed into dense, stable configurations. Even filaments, though they stretch and thin over time, contain enough matter for gravity to remain a significant restraining force on expansion. In voids, gravity is weak. The matter density is so low that gravitational attraction between the sparse galaxies and diffuse gas clouds becomes negligible compared to the other force at play: dark energy. Dark energy is the mysterious component that makes up approximately 68% of the total energy content of the universe according to current measurements. Its fundamental nature remains unknown. It could be a cosmological constant, an inherent and unchanging property of space itself. It could be a dynamic field that varies in strength over time and space. Whatever it is, it behaves as a repulsive pressure that accelerates the expansion of space. In dense regions, gravity can counterbalance this pressure and hold matter together against the expansion. In voids, there is simply not enough matter for gravity to compete. Dark energy runs the show unchallenged. The consequence is that voids expand faster than the cosmic average. They grow like bubbles in rising dough, pushing their boundaries outward into the surrounding filaments and walls. As the void expands, its interior becomes even less dense, which further weakens gravity, which allows even faster expansion driven by dark energy. This is a self-reinforcing cycle that has been running for billions of years and continues today. The emptier a void becomes, the faster it empties further. The cycle never reverses because there is no mechanism to inject new matter into a void once it has begun expanding. Matter only leaves. It never returns. Over billions of years, this process hollows out voids progressively, making them larger and more diffuse while the matter they shed accumulates along the filaments and walls at their edges. The dense regions get denser. The empty regions get emptier. The contrast between the cosmic web and the voids sharpens over time, and that contrast will continue sharpening for as long as dark energy continues driving expansion. This expansion has measurable consequences for how galaxies move near void boundaries. Galaxies located near the edges of voids are observed to be moving outward, away from the void center, faster than the cosmic expansion alone would predict. They are responding to a gravitational imbalance. All the dense material lies outside the void, concentrated in the surrounding filaments and clusters. That exterior matter pulls on the void edge galaxies more strongly than the sparse interior, accelerating them outward, away from the void center and toward the denser structures beyond. This outflow pattern is systematic and observable. Astronomers can track it using redshift measurements combined with independent distance estimates. It provides direct evidence that voids are not static features frozen in place since the early universe. They are dynamic, growing, actively reshaping the distribution of matter around them in real time. The expansion also leaves a signature in the oldest light in the universe. When photons from the cosmic microwave background travel through a void on their way to our telescopes, they experience an effect called the integrated Sachs-Wolf effect. As a photon enters a void, it falls into a region of lower gravitational potential, gaining a tiny amount of energy. As it exits the void on the other side, it climbs back out, losing energy. In a universe where the gravitational potential remains constant, these two effects cancel perfectly, and the photon arrives unchanged. But because the void is expanding while the photon passes through it, driven by dark energy, the gravitational potential weakens during the transit. The void the photon exits is slightly shallower than the void it entered. The cancellation is imperfect. The photon arrives with marginally less energy than it started with, which registers as a tiny temperature decrease in the cosmic microwave background in the direction of the void. This effect is small for any individual void, typically only a few millionths of a degree. But when astronomers stack observations from many known void locations identified through galaxy surveys and compare the average cosmic microwave background temperature in those directions to the overall average, they find a consistent signal. Void directions are slightly cooler, the correlation is statistically significant and matches theoretical predictions from Lambda-CDM. It provides independent, elegant confirmation that voids affect the cosmic microwave background in exactly the way physics says they should. The voids are not invisible. They leave fingerprints in the oldest light in the universe. For ordinary voids, none of this is a problem. The integrated Sachs-Wolf signal from a typical void falls comfortably within the range Lambda-CDM predicts. The outflow velocities at void edges match simulations. The size distribution of small and medium voids agrees with theoretical expectations. The standard model handles ordinary voids gracefully. It explains why they exist, how they form, how they grow, and what signatures they leave in both the cosmic microwave background and in galaxy velocity fields. Voids are a success story for the standard model, not a challenge to it. But the standard model's comfort with voids depends critically on those voids staying within certain statistical bounds. The model predicts a ceiling on void size and depth, not a hard cutoff, but a probabilistic one that grows increasingly severe. The larger and emptier a void becomes, the less likely it is under standard initial conditions and standard gravitational physics. At some point, the probability drops so low that finding such a void in the observable universe would be a genuine surprise, not a violation of physics, not an impossibility in any absolute sense, but a result unusual enough to demand explanation, a result that would force scientists to ask hard questions, whether the model is missing something fundamental, whether the initial conditions from inflation were different than what standard theory assumes, whether gravity works differently at the largest scales, or whether the void is simply not as extreme as it appears when measured more carefully. This is the boundary where voids stop being routine features of cosmic structure and start becoming scientific tensions. It is not a sharp line. It is a gradient, a region of increasing statistical discomfort where the observed properties of a structure begin to strain the predictions of the model that is supposed to explain it. And the strain increases with every additional megaparsec of diameter, with every additional percentage point of density deficit, with every additional measurement confirming that the void is real, coherent, and not an artifact of incomplete observation. The cosmic web is full of voids. Most of them are modest in scale and perfectly consistent with Lambda-CDM. They are the expected consequences of gravitational instability, dark energy dominance in underdense regions, and nearly 14 billion years of cosmic evolution. They are the dark spaces between the bright threads, the negative image of the structure that contains all the mass and all the action. They are as normal and expected as the filaments themselves. They are built into the blueprint of the universe from its first moment. But not all voids are normal. Some are large enough, empty enough, and well characterized enough to sit at the uncomfortable edge of what the standard model can naturally produce. These are the supervoids, the structures where emptiness itself becomes a source of scientific tension, and among them, one has stood out for more than 4 decades. It was discovered in 1981 by a team of astronomers who were not looking for emptiness at all. They were counting galaxies, mapping structure, measuring positions. What they found instead was a region of space so barren, so vast, and so anomalous that it has remained one of the most striking features in every large-scale map of the universe produced since. It sits in the direction of the constellation Boötes, roughly 700 million light-years from Earth. It stretches approximately 330 million light-years across. It contains roughly 60 galaxies where approximately 2,000 should exist. And more than 4 decades after its discovery, cosmologists are still debating whether the standard model of the universe can fully account for how it got there. What comes next is the story of the Boötes Void itself, how it was found, what it looks like from the inside, and why its sheer scale began to make cosmologists deeply uncomfortable. The year was 1981. The discipline of observational cosmology was still young in any modern sense. Astronomers had only recently begun mapping the three-dimensional positions of galaxies in earnest, converting the flat projections of the night sky into genuine spatial charts showing where things actually were in the depth of the cosmos. It was painstaking work. Every galaxy required an individual spectrum, captured by pointing a telescope at it for long enough to split its light into component wavelengths and measure the precise redshift. There were no automated fiber-fed spectrographs covering hundreds of galaxies at once. There were no digital sky surveys operating around the clock. Each data point was earned one observation at a time, one telescope pointing at a time, one night at a time. Progress was slow, but the results were already beginning to transform how astronomers understood the universe. The first generation of redshift surveys had revealed tantalizing hints that galaxies were not scattered randomly through space. They clumped, they gathered into structures, and between those structures, there appeared to be gaps, regions where galaxies were far less common than expected. But nobody yet understood how large those gaps could get. Robert Kirshner, along with Augustus Oehmler, Paul Schechter, and Stephen Schechtman, was conducting exactly this kind of survey. Working from observations gathered at multiple observatories, the team was measuring galaxy redshifts in several directions across the sky, probing the distribution of matter at distances of hundreds of millions of light-years. The goal was straightforward: map where the galaxies are, understand the large-scale structure, contribute data points to an emerging picture of how the universe organizes itself. What they found in the direction of the constellation Boötes was not what anyone expected. In their survey fields pointing toward Boötes, the galaxies simply stopped. Not gradually, not as a gentle thinning of the distribution, but as a stark and dramatic absence. Where their other survey fields showed the expected scatter of galaxies at various distances, the Boötes fields showed a gap, a huge gap. A gap that extended across an enormous range of redshifts, corresponding to a vast three-dimensional volume of space. The team identified a region stretching tens of megaparsecs across where essentially no galaxies appeared in their redshift range. The volume was enormous, and it was almost completely empty. It was as though someone had taken a colossal sphere-shaped cookie cutter and removed a section of the cosmic web, leaving behind only the faintest traces of structure. The initial reaction was cautious disbelief. The first instinct of any careful scientist finding an unexpected result is to suspect the data. Perhaps the survey was incomplete in that direction. Perhaps dust was obscuring the view, blocking more distant galaxies from detection. Perhaps there was a systematic error in the redshift measurements that created an artificial gap. Perhaps foreground stars were contaminating the observations, making it harder to identify faint background galaxies. Kirshner and his colleagues tested these possibilities methodically and systematically. They checked for foreground obscuration by examining the sky in multiple wavelengths. They verified that their survey depth was consistent across different fields. They compared their results with other existing catalogues to ensure consistency. They confirmed that the absence was real. The galaxies were not hidden behind dust. They were not masked by intervening material. They were not lost in the noise of imperfect measurements. They were simply not there. The volume was genuinely, dramatically, unexpectedly empty. The team published their findings. and the astronomical community began to reckon with the existence of what would become known as the Boötes Void. Sometimes called the Great Void or the Great Nothing, it quickly became one of the most discussed features in extragalactic astronomy. Not because it was the first void ever identified. Voids had been recognized in galaxy surveys since the late 1970s, and by 1981, several significant underdensities had been documented. But the Boötes Void exceeded anything previously observed by a wide margin. Its sheer scale set it apart from every other known void and forced astronomers to confront the possibility that the universe could produce empty regions far larger than anyone had anticipated. Subsequent surveys refined the picture. The Boötes Void is approximately spherical, centered at a distance of roughly 700 million light-years from Earth in the direction of the constellation Boötes. Near right ascension, 14 hours, 50 minutes, and declination 46 degrees. Its diameter measures approximately 330 million light-years, which corresponds to a radius of about 62 megaparsecs. In a volume of that size, based on the average density of galaxies in the observable universe, astronomers would expect to find roughly 2,000 galaxies. The actual count stands at approximately 60. Let those numbers settle for a moment. 60 galaxies where 2,000 should be. That is not a mild underdensity. That is not a region where the galaxy count dipped modestly below the cosmic average. The kind of fluctuation you might expect from ordinary statistical variation. That is a 97% deficit. 97 out of every 100 galaxies that should exist in that volume, based on the universe's mean density, are simply absent. The void is not slightly empty. It is almost perfectly empty. It represents one of the most extreme underdensities ever confirmed in the observable universe, a region where the normal rules of cosmic population seem to have been suspended. The void is also not a featureless blank. Observations have revealed that the roughly 60 galaxies found within it are not scattered randomly throughout the volume. Many of them concentrate along a tube-shaped filament that runs through the interior, connecting structures on opposite sides. This internal filament is thin and faint by cosmic standards, containing far fewer galaxies than a typical filament of comparable length in the denser regions of the cosmic web. But its presence is scientifically significant. It suggests that the Boötes Void is not a perfectly pristine empty sphere. It has internal structure, hints of the cosmic web persisting even in this extreme environment. The filament may represent a remnant of the original structure that existed before the void expanded and emptied, a fossil thread left behind as matter drained outward over billions of years. Or it may indicate that the Boötes Void is not a single monolithic structure, but rather the product of several smaller voids that merged together over cosmic time, with the filament being a wall between formerly separate voids that has not yet fully dissolved. This question, whether the Boötes Void is one giant structure or a collection of merged smaller structures, remains scientifically relevant. Lambda-CDM simulations produce large voids primarily through hierarchical merging. Small voids form first from modest initial underdensities. As the universe evolves, neighbouring small voids expand into each other. Their dividing walls thin and break apart, and the result is a single larger void. This process is well understood and well simulated, and it is the primary mechanism by which the universe produces its largest voids. The question for the Boötes Void is whether hierarchical merging alone can produce something this large and this empty in the 13.8 billion years available since the Big Bang, or whether additional factors are needed to explain it. The void's boundaries add another layer of complexity. Unlike a soap bubble with a sharp surface, the Boötes Void does not have a clean edge. Its density increases gradually as you move outward from the centre toward the surrounding cosmic web. The transition zone, where the void's interior meets the filaments and walls around it, stretches across tens of millions of light-years. Defining exactly where the void ends and normal density space begins is a matter of convention rather than sharp physical demarcation. Different researchers using different density thresholds to define the boundary will arrive at somewhat different size estimates. The 330 million light-year figure represents the most commonly cited diameter, based on where the galaxy density drops to a level dramatically below the cosmic mean, but the true extent of the underdensity may be somewhat larger or smaller depending on how the measurement is performed. Despite these uncertainties, the basic picture is robust and has been confirmed by multiple independent surveys over more than 4 decades. The Boötes Void is real, it is enormous, and it is extraordinarily empty. No serious astronomer disputes its existence. The debates concern its precise properties and their implications, not whether it is there. One of the most vivid illustrations of what the void means comes from astronomer Greg Aldering, who calculated what the universe would look like if the Milky Way were located at the center of the Boötes Void, rather than in its actual position within the cosmic web. The result is haunting. If our galaxy sat at the heart of the Great Nothing, surrounded on all sides by 330 million light-years of near-total emptiness, the night sky beyond our local galactic neighborhood would have been almost completely dark for most of human history. No galaxy outside our own local group would have been visible to any telescope built before the middle of the 20th century. The Andromeda Galaxy, our nearest large neighbor at 2.5 million light-years, would still be visible because it is gravitationally bound to us and would presumably have accompanied us into the void. But the next nearest large galaxies would lie hundreds of millions of light-years away, far beyond the reach of any instrument available before the era of modern electronic detectors. Humanity would not have discovered the existence of other galaxies until the 1960s at the earliest. The great debate of the 1920s, when astronomers argued over whether the Milky Way was the entire universe or just one island among many, would never have happened in that form. There would have been nothing to debate. The sky would have offered no evidence that anything existed beyond our own galaxy and its immediate companions. The concept of an expanding universe, discovered through the observation of receding galaxies, might have been delayed by decades or might have required entirely different evidence to establish. Edwin Hubble's great contribution, the discovery that distant galaxies are receding from us at speeds proportional to their distance, would have been impossible because there would have been no distant galaxies visible to measure. Cosmology as we know it would have developed along a fundamentally different trajectory, perhaps arriving at the same truths eventually through the cosmic microwave background or other evidence, but decades later and by a much harder road, all because of emptiness, all because of the accident of location. This thought experiment is more than a curiosity. It illustrates a deep and underappreciated point about the relationship between cosmic environment and scientific knowledge. The cosmology we have built over the past century depends heavily on the fact that we live in a moderately dense region of the cosmic web, surrounded by enough galaxies at enough distances to measure expansion, test models, and map structure. Our position gives us access to a rich dataset of nearby galaxies, galaxy clusters, and large-scale structures that collectively provide the evidence base for modern cosmology. If our cosmic address were different, if we happened to inhabit a void rather than a region near filaments and clusters, our understanding of the universe would be dramatically impoverished. The information simply would not be available to us. We would be prisoners of our environment, cosmologically isolated, unable to see the larger cosmos because it would be too far away and too faint to detect with any reasonable technology. The universe would still be vast and structured. We just would not know it. The galaxies that do exist within the Boötes Void are themselves remarkable objects, shaped by their extreme isolation. Void galaxies live fundamentally different lives from galaxies in the dense filaments and clusters of the cosmic web. In a typical cluster environment, galaxies interact constantly. They pass near each other, exchange gravitational tugs, sometimes collide and merge outright. These interactions trigger bursts of star formation as gas clouds compress and collapse. They strip gas from smaller galaxies, leaving them depleted and quenched. They feed supermassive black holes at galactic centers, powering active galactic nuclei that blast jets of energy into the surrounding space. The cluster environment is violent, dynamic and transformative. Galaxies that enter clusters emerge changed, often converted from blue, star-forming spirals into red, dead ellipticals through a combination of gas stripping, tidal disruption, and mergers. Void galaxies experience none of this. They evolve in near-perfect isolation. The nearest neighbour might be tens of millions of light-years away, so distant that the gravitational influence between them is effectively zero on any timescale shorter than the age of the universe. Without external disturbance, void galaxies follow their own internal evolutionary paths, shaped by their own gas supply, their own dark matter halo, their own stellar populations, and nothing else. They are the most self-contained systems in the cosmos, evolving according to intrinsic physics alone without the complicating influence of environment. The observational consequences of this isolation are measurable and consistent across surveys. Void galaxies tend to be smaller and less massive than galaxies in filaments. They are predominantly late-type systems, meaning spirals and irregular galaxies rather than ellipticals. This makes sense because elliptical galaxies form primarily through major mergers, which require close neighbours. Without mergers, galaxies retain their disk structures and spiral arms indefinitely. Some void galaxies display remarkably smooth and undisturbed morphologies, with clean rotation patterns and well-organised spiral structure that has never been disrupted by a passing companion or a tidal encounter. Their disks are thinner, their arms more regular, their overall appearance more serene than galaxies of comparable mass in the crowded corridors of the cosmic web. They are pristine laboratories for studying how galaxies evolve when left entirely to their own devices, when all the noise and violence of environment is stripped away and only the internal physics remains. Void galaxies also tend to be bluer than their counterparts in denser environments, indicating ongoing star formation. This may seem counterintuitive. One might expect that galaxies in emptier regions would form fewer stars because they have less material to work with, but the explanation lies in gas retention. In dense environments, interactions with neighbours and with the hot intracluster medium can strip gas from galaxies, cutting off the fuel supply for star formation. In voids, galaxies retain their gas. They hold onto large reservoirs of neutral hydrogen that have never been depleted by external processes. Star formation proceeds slowly but steadily over billions of years, fueled by this preserved gas supply. When internal processes occasionally trigger a burst of more intense star formation, perhaps through disk instabilities or gas accretion from the intergalactic medium, the galaxy has ample fuel available. The result is that a surprisingly high fraction of void galaxies are starburst systems, experiencing intense but short-lived episodes of rapid star formation that would be less common in environments where the gas has already been stripped away. The chemical composition of void galaxies provides another window into their isolated evolution. Stars create heavy elements through nuclear fusion and scatter them into space when they die. Each generation of stars incorporates more of these heavy elements, gradually enriching the galaxy's overall chemical composition over time. This process, called chemical evolution, should proceed more slowly in void galaxies because their star formation rates are lower. With fewer stars forming and dying per unit time, the enrichment progresses at a more leisurely pace. Observations broadly confirm this expectation. Void galaxies tend to have lower metallicities than galaxies of comparable mass in denser environments, meaning they contain lower abundances of elements heavier than helium. However, the difference is not as dramatic as the simplest models predict. Some void galaxies show chemical enrichment levels surprisingly close to those of normal environment galaxies, suggesting that the interplay between gas inflow, outflow, and star formation is more complex than isolation alone would imply. The dark matter halos surrounding void galaxies are also distinctive and scientifically valuable. Every galaxy is embedded in a halo of dark matter that extends far beyond the visible stars and gas, typically reaching distances many times the optical radius of the galaxy itself. In dense environments, these halos are subject to tidal forces from neighbouring halos, which can strip away outer material, distort their shapes, and create complex substructure through interactions. In voids, halos remain relatively undisturbed. They are more spherical, more extended, and more regular in their density profiles than halos in clusters or filaments. This makes void galaxies particularly useful for testing dark matter models because their halos are less contaminated by environmental effects. The gravitational signature of the halo can be measured more cleanly, providing better constraints on the mass, concentration, and inner structure of dark matter distributions than is possible in busier environments. Below a certain halo mass, roughly corresponding to a circular velocity of about 35 km per second, dark matter halos in voids lack sufficient gravity to retain gas effectively. Gas needs to cool and collapse to form stars, and cooling is less efficient in shallow gravitational wells. The shallowest halos cannot form stars at all. They exist as dark halos, containing only dark matter and no visible galaxy. This threshold explains why voids are not filled with enormous numbers of tiny dwarf galaxies. The halos are there, predicted by Lambda-CDM and presumably present throughout the void volume, but most of them remain dark, invisible to any telescope that detects light. The roughly 60 visible galaxies in the Boötes Void represent only the most massive systems, those whose halos were deep enough to accumulate and retain gas despite the void environment. Beneath them lies a population of dark halos that may number in the thousands or tens of thousands, filling the void with invisible gravitational scaffolding that no optical survey can see. The Boötes Void does not exist alone among extreme underdensities. Several other large voids have been catalogued across the observable universe, though none quite matches its combination of size and emptiness. The local void, first identified by Brent Tully and Richard Fisher, sits adjacent to our own galaxy group and stretches approximately 200 million light-years across. It is the void nearest to us, an enormous empty region bordering our cosmic neighbourhood, and its gravitational influence contributes measurably to the motion of our galaxy through space. The Milky Way and its neighbours in the local sheet are observed to be moving away from the local void at approximately 260 km per second, pushed outward by the gravitational pull of denser material on the void's far side. The Taurus void is a roughly circular underdensity about 100 million light-years in diameter, adjacent to the Perseus-Pisces supercluster. A handful of galaxies have been found within it, including objects that appear to be slowly and quietly evolving in their extreme and profound isolation. Other notable voids include the Sculptor void, the Microscopium void, and the northern and southern local supervoids identified through galaxy surveys and cosmic microwave background analysis. Each of these structures represents a significant underdensity, a region where the galaxy count falls well below the cosmic average, but their sizes generally range from 100 to 200 million light-years in diameter. The Boötes Void, at approximately 330 million light-years, exceeds the typical upper range of commonly observed voids. It is not merely a large void, it is among the very largest confirmed voids ever identified in any survey. Whether the Boötes Void is truly the single largest void in the observable universe is a question that depends on how you define and measure voids, and on whether certain candidate structures are confirmed. The KBC Void, named for Keenan, Barger and Cowie, who characterized it in 2013, describes a much larger underdensity, roughly 2 billion light-years across, centered approximately on our own galaxy's location. If the KBC Void is real and as deep as some measurements suggest, it would dwarf the Boötes Void in raw size. But the KBC Void is a different kind of structure. Its density deficit is estimated at roughly 20% below the cosmic mean, far less severe than the 97% galaxy deficit within the Boötes Void. The KBC Void is a subtle, broad underdensity spread across an enormous volume. The Boötes Void is a concentrated, dramatic emptiness packed into a smaller but far more extreme region. They represent different regimes of the void phenomenon. The Eridanus Supervoid, another candidate structure we will examine shortly, may extend roughly 1.8 billion light-years across, but again with a more moderate density contrast than the stark emptiness of Boötes. The Boötes Void remains exceptional, not because it is necessarily the largest void in every possible measurement, but because no other confirmed structure of comparable size achieves such an extreme and dramatic level of emptiness. This distinction matters for the science. A broad, shallow underdensity like the KBC void raises questions about local measurement bias and the Hubble tension. A deep, concentrated emptiness like the Boötes void raises different questions about the efficiency of structure formation and the probability of extreme voids arising from standard initial conditions. The two types of structure test different aspects of cosmological models, even though both fall under the general category of cosmic voids. The longevity of the Boötes void as a subject of scientific interest is itself noteworthy. Discovered in 1981, it has now been studied for more than 4 decades. In that time, galaxy surveys have grown from samples of thousands of galaxies to samples of millions. Telescopes have improved by orders of magnitude in sensitivity and sky coverage. Computational simulations have gone from crude approximations with a few thousand particles to sophisticated models tracking billions of particles across cosmological volumes. And through all of this advancement, the Boötes void has remained. It has not been explained away as an artifact of incomplete data. It has not been filled in by deeper surveys finding hidden galaxies. It has not been subdivided into smaller, less remarkable structures by higher resolution mapping. The void has survived every improvement in observational capability that has been thrown at it. Each new survey confirms its basic properties. The void is there. It is as large and as empty as early observations suggested. Every generation of improved technology has only confirmed what Kirshner and his colleagues first reported. This persistence is important because it eliminates one of the most common and most reasonable objections to anomalous astronomical discoveries. When something unusual appears in a survey, the default assumption is always that better data will make it go away. The anomaly might be a statistical fluke in a small sample. It might be an artifact of the survey's selection criteria or observing strategy. It might disappear when observed with different instruments or at different wavelengths. It might shrink in significance when a larger and more representative sample is compiled. The Boötes void has passed all of these tests over the course of 4 decades. It shows up in optical surveys, in infrared surveys, in redshift catalogues compiled by entirely independent teams using different telescopes, different techniques, and different analysis methods. Its reality is not in question. The data are unambiguous and consistent across every survey that has examined it. What remains in question is what it means. The Boötes void is real, enormous, and strikingly empty. It contains a tiny fraction of the galaxies expected for its volume. Its interior shows traces of structure, a thin filament threading through otherwise vacant space, suggesting a complex formation history that may involve the merging of smaller voids over cosmic time. Its galaxies are isolated, gas-rich, chemically underdeveloped, and morphologically pristine. Its boundaries fade gradually into the surrounding cosmic web, and it has withstood more than 40 years of increasingly precise observation without fading in importance or shrinking in measured extent. But the discovery of the void was only the beginning of the story. The deeper question, the one that continues to occupy cosmologists today, is not what the Boötes void looks like. It is whether its existence is consistent with what our best models of structure formation predict should be possible. The standard model of cosmology was built to explain precisely this kind of cosmic architecture. For most structures across most of the observed size range, it succeeds with remarkable fidelity, predicting what surveys find before the surveys find it. But every model has limits. Every framework has edges beyond which its predictions become uncertain or strained. And the Boötes void sits precisely at that edge, occupying the region of parameter space where the standard model's predictions become uncomfortable, where the numbers start to look improbable, where the question shifts from what is the void to how did the universe build something, this empty, this large, this extreme. And beyond the Boötes void, another enormous emptiness waits, one that was discovered not by counting galaxies but by reading a cold whisper in the oldest light in the universe. That tension, between what the void is and what the models say it should be, is where the real story begins. The Boötes Void is real. That much is settled. Decades of observation have confirmed its existence, measured its extent, catalogued its sparse population of galaxies, and mapped its gradual boundaries. The question that remains is harder and more consequential. Can the standard model of cosmology explain it? This is not an abstract concern. The standard model, Lambda-CDM, is the most successful scientific framework ever constructed for describing the large-scale universe. It explains the temperature fluctuations in the cosmic microwave background with extraordinary precision. It accounts for the observed abundances of hydrogen, helium, and lithium forged in the first minutes after the Big Bang. It predicts the statistical distribution of galaxies across the cosmic web in ways that match observations to a remarkable degree. It correctly describes the accelerating expansion of the universe driven by dark energy. It provides a coherent account of how dark matter seeded the gravitational collapse that produced every galaxy, every cluster, and every filament we observe today. Lambda-CDM is not a speculative idea. It is the consensus framework of modern cosmology, supported by multiple independent lines of evidence converging on the same picture. When this model makes a prediction, scientists take it seriously. And when an observation appears to conflict with those predictions, the conflict demands careful examination. Lambda-CDM makes specific quantitative predictions about cosmic voids. It predicts their existence, which is confirmed. It predicts that they should occupy the majority of the universe by volume, which is confirmed. It predicts that their interiors should be dominated by dark energy rather than gravity, which is confirmed through observations of void expansion rates and the integrated Sachs-Wolf effect. It predicts the statistical distribution of void sizes, the mathematical relationship between void depth and void radius, and the rate at which voids should grow over cosmic time as dark energy increasingly dominates the expansion. For small and medium voids, these predictions match observations beautifully. The model works across the normal range of void properties. The physics is sound, the mathematics is precise, and the agreement with data is impressive. The difficulty arises at the extremes of the distribution. Lambda-CDM predicts that very large voids should be very rare. The prediction follows directly from the initial conditions. The density fluctuations imprinted during inflation follow a well-measured power spectrum. Large-scale fluctuations, the kind needed to seed very large voids, have lower amplitude than small-scale fluctuations. This means that the initial underdensities required to eventually produce a void, 330 million light-years across and 97% empty of galaxies, would need to be unusually deep and unusually extended in the primordial density field. Such configurations are not forbidden by the model. They are simply improbable. They exist in the far tail of the statistical distribution, where probability drops sharply with increasing size and depth. How improbable depends on the details. Estimating the exact rarity of a void like Boötes requires comparing it to the void populations produced in large cosmological simulations. These simulations generate virtual universes by starting from the measured initial conditions, applying the known laws of physics, and evolving the matter distribution forward through the full span of cosmic time since the Big Bang. Researchers then search the simulated volumes for voids matching the observed properties of the Boötes Void. The results vary depending on the simulation, the void-finding algorithm used, and how precisely the comparison is made. But the general finding is consistent. Voids as large and as empty as Boötes are uncommon in Lambda-CDM simulations. They appear, but rarely. Some analyses find them in perhaps 1 out of every several hundred simulated volumes comparable in size to the observable universe. Others find them even less frequently. This rarity is not by itself a crisis. Rare things happen. The observable universe is enormous, containing a vast number of independent volumes in which structure has formed. If a void like Boötes has a probability of 1 in several hundred per observable universe-sized volume, and we have surveyed a reasonable fraction of our observable volume, Finding one is unusual but not shocking. It would be like rolling a pair of dice and getting double sixes. Unlikely on any single roll, but hardly miraculous given enough attempts. The discomfort comes from a different direction. It comes from the accumulation of structures at the extreme end of the distribution. The Boötes Void is not the only oversized structure that has challenged Lambda-CDM expectations. The Sloan Great Wall, stretching 1.4 billion light-years, pushed the boundaries of what filamentary structures should achieve. The Shapley supercluster, one of the most massive concentrations of matter in the nearby universe, exceeds typical predictions for supercluster richness. The Hercules Corona Borealis Great Wall, if confirmed at its reported size of roughly 10 billion light-years, would dramatically violate the expected homogeneity scale. Each of these structures individually might be a tolerable statistical outlier. Taken together, they begin to suggest a pattern. The universe may contain more extreme structures, both overdense and underdense, than Lambda-CDM comfortably produces from standard initial conditions. The Boötes Void is one data point in this larger conversation about whether the standard model underestimates the variance of cosmic structure on the largest scales. But the Boötes Void is not alone among extreme voids. There is another candidate, discovered through an entirely different method, that pushes the tension even further. In 2004, researchers analysing data from the Wilkinson Microwave Anisotropy Probe, which had produced the most detailed full-sky map of the cosmic microwave background radiation ever made, identified something unexpected. The map had revealed the expected pattern of tiny temperature fluctuations imprinted when the universe was 380,000 years old, the seeds of all future structure formation, stretched across the sky in a mottled pattern of warm and cool spots at various angular scales. But the 2004 analysis also revealed something else. In the southern sky, in the direction of the constellation Eridanus, there was a cold spot. Not just a slightly cool region of the kind that appears routinely in the cosmic microwave background as part of its normal statistical variation. This was an unusually large, unusually cold patch, roughly 5 degrees across on the sky, approximately 70 millionths of a degree cooler than the average cosmic microwave background temperature. Compared to the typical root mean square temperature fluctuation of about 18 millionths of a degree, the cold spot was striking. Its combination of angular size and temperature deficit made it a statistical outlier, appearing in only a small percentage of simulated cosmic microwave background skies generated from Lambda-CDM initial conditions. The cold spot immediately attracted scientific attention and a variety of proposed explanations. Some researchers suggested it was simply a rare but expected fluctuation in the primordial cosmic microwave background, a statistical tail event that would appear in a few % of random realizations. Others proposed more exotic origins, including the possibility that it represented a signature of a collision between our universe and another universe in a multiverse, an idea that generated significant public interest but limited scientific support. A third explanation, more conventional and more testable, proposed that the cold spot was not primordial at all. Instead, it might be the imprint of a massive foreground supervoid lying between us and the cosmic microwave background, cooling the passing photons through the integrated Sachs-Wolf effect. This third explanation motivated astronomers to search for a void in the direction of the cold spot, and they found one. Galaxy surveys covering the Eridanus region revealed a significant underdensity at relatively low redshift, centered at a distance of roughly 3 billion light-years from Earth. This structure, which came to be called the Eridanus Supervoid, extends approximately 1.8 billion light-years across, making it one of the largest individual underdensities ever identified. Its density deficit is estimated at roughly 20% below the cosmic mean, comparable to the broad underdensity reported for the KBC void, but extending over an enormous volume. The Eridanus Supervoid is not as dramatically empty as the Boötes Void on a per-volume basis. Its galaxy deficit is moderate rather than extreme, but its sheer physical size makes it significant. The conformation of the Eridanus Supervoid came through multiple independent analyses carried out by different research teams using different datasets and different methodologies. In 2015, a team led by Istvan Sapudi used data from the Pan-STARRS optical survey and the WISE infrared survey to detect the supervoid as a statistically significant underdensity aligned with the cold spot direction. This initial detection was important because it established the existence of a foreground structure that could plausibly contribute to the cold spot anomaly through known physics. Subsequent work using data from the Dark Energy Survey strengthened the detection considerably and placed it on firmer statistical ground. The DES Year 3 analysis, published in 2022, used a catalogue of luminous red galaxies to confirm the Eridanus Supervoid as a significant underdensity at redshifts below approximately 0.2. This galaxy survey, combined with the Eridanus Supervoid's alignment with the cold spot, strongly suggests that the two structures are physically connected. The same analysis showed, with greater than 5 sigma significance, that the Eridanus Supervoid appears as the single most prominent large-scale underdensity in dark matter mass maps reconstructed from DESI gravitational lensing data. This was a robust detection using 2 independent traces of large-scale structure, galaxy positions and dark matter lensing, both pointing to the same conclusion. The supervoid is real. But here is where the story becomes complicated. The integrated Sachs-Wolf effect from a void of the Eridanus supervoid's measured size and depth, calculated using standard Lambda-CDM physics, can account for only about 10 to 20% of the cold spot's observed temperature deficit. The void is real, and it does produce a temperature imprint in the cosmic microwave background, but the imprint is too small. Standard physics predicts that a void with a 20% density deficit extending roughly 200 megaparsecs in radius should produce a temperature decrement of approximately 10 millionths of a degree. The observed cold spot is roughly 70 millionths of a degree cold. The supervoid explains a fraction of the signal, but not all of it. This mismatch has several possible explanations, none of them fully satisfying. The first possibility is that the cold spot is a combination of 2 effects: a moderate integrated Sachs-Wolf imprint from the Eridanus supervoid, plus a chance alignment with a genuinely cold fluctuation in the primordial cosmic microwave background. In this scenario, neither effect alone is particularly extreme, but their coincidental alignment produces the observed anomaly. This explanation is statistically reasonable. Chance alignments do occur, but it requires accepting a coincidence, which some researchers find unsatisfying. The second possibility is that the Eridanus supervoid is larger, deeper, or more complex than current measurements indicate. Galaxy surveys at that distance are less complete than nearby surveys. Faint galaxies and low surface brightness structures could be missed, leading to an underestimate of the void's true density deficit. If the void is actually 30% underdense rather than 20%, or if it extends further than current measurements suggest, the predicted integrated Sachs-Wolf signal would increase. Future surveys with greater depth and sky coverage will test this possibility. The third possibility is the most scientifically provocative. The integrated Sachs-Wolf effect from supervoids may be intrinsically stronger than Lambda-CDM predicts. This is not a hypothetical concern. It is based on actual measurements. Analyses stacking the integrated Sachs-Wolf signal from many known supervoids identified in galaxy surveys have found that the average signal is approximately 5 times stronger than Lambda-CDM predicts. The DES analysis reported a combined excess ISW amplitude of roughly 5.2 plus or minus 1.6 times the expected Lambda-CDM value, using supervoids identified in both the BOSS and DESI surveys across a redshift range of 0.2 to 0.9. If this excess is real and not a systematic artifact of the analysis pipeline or the void identification method, it suggests that something about the standard model's treatment of void physics is incomplete. Either the gravitational physics governing void evolution differs from general relativity on the largest scales, or the properties of dark energy within voids differ from the simple cosmological constant assumption or some other physical mechanism enhances the integrated Sachs-Wolf signal beyond what standard calculations predict. Any of these explanations would represent a significant departure from the current consensus and would have profound implications for our understanding of the dark sector of the universe. This finding remains debated within the cosmological community, and for good reason. Other analyses using CMB lensing as an independent probe of the same supervoids did not find a corresponding excess in the lensing signal. Since gravitational lensing and the integrated Sachs-Wolf effect both depend on the gravitational potential of the supervoid, but in different ways, a discrepancy between them is puzzling. If the gravitational potential were genuinely stronger than expected, both signals should be enhanced. The fact that only the ISW signal appears anomalous suggests the situation is more nuanced than a simple modification to gravity. It could reflect subtle observational systematics, or it could point toward new physics that affects photon energy differently from photon path bending. The scientific community has not reached consensus on this question. The Eridanus Supervoid and the Boötes Void test different aspects of the standard model, but they converge on the same broad and important concern. The Boötes Void challenges the model's predictions for how empty a region of space can become within the available cosmic time given standard initial conditions. The Eridanus Supervoid challenges the model's predictions for how large a coherent underdensity can grow and how strongly it should affect the cosmic microwave background through the integrated Sachs-Wolf effect. Together, they represent two independent pieces of evidence suggesting that the extreme end of void properties may not be fully captured by Lambda-CDM in its standard form. It is important to state clearly what this does and does not mean. It does not mean Lambda-CDM is wrong. The model remains spectacularly successful across the vast majority of its predictions. Nothing about the extreme void population invalidates the framework that correctly describes everything from the primordial element abundances to the clustering of galaxies at intermediate scales. What the extreme voids suggest is that the model may be incomplete at the margins. The tails of the distribution, the rare extreme structures, may behave differently from what the standard framework predicts. This is not unusual in physics. Models often work beautifully in the central regime and show strain at the boundaries. The strain does not invalidate the model. It indicates where new physics or refined understanding may be needed. Several theoretical avenues have been proposed to address this strain, and each carries different implications. The first avenue involves modifying the initial conditions. If the power spectrum of primordial density fluctuations contains slightly more power at large scales than the standard nearly scale invariant spectrum predicts, larger initial underdensities would be more common, and the formation of very large voids would become less improbable. This could happen if the physics of cosmic inflation were slightly different from the simplest models. Some inflationary models predict features in the power spectrum, bumps or tilts at specific scales, that could enhance large-scale structure formation. Testing this requires extremely precise measurements of the cosmic microwave background at large, angular scales, and careful comparison with the statistics of large-scale structure. Current data do not definitively support or rule out such features, but future measurements may provide clearer constraints. The second avenue involves modifying gravity. If gravity behaves differently on cosmological scales than general relativity predicts, the growth of structure could be enhanced across the board, making large voids and massive superclusters more common than standard calculations suggest. Modified gravity theories, including certain classes of scalar tensor theories and theories inspired by Milgromian dynamics, predict more efficient structure formation at large scales because the effective gravitational force is stronger in low acceleration or low density environments. Some of these theories can produce void populations that naturally include Boötes-scale structures without requiring unusual initial conditions or statistical luck. The voids simply form more easily when gravity is stronger on the relevant scales. However, modified gravity theories must also explain every other successful prediction of general relativity, from solar system dynamics to the orbital decay of binary pulsars to the gravitational wave signals detected by LIGO and Virgo, from merging black holes and neutron stars. This is a high bar, and most modified gravity theories struggle to match the full range of observational constraints simultaneously. The third avenue involves the properties of dark energy. If dark energy is not a simple cosmological constant, but varies in strength over time or space, the growth of voids could be affected in ways that standard Lambda-CDM does not capture. Recent results from the Dark Energy Spectroscopic Instrument, based on its first year of data released in 2024, provided some of the most precise measurements ever made of the cosmic expansion history using baryon acoustic oscillations. Some analyses of this data hinted at the possibility that dark energy's equation of state may have varied over time, though the results remained consistent with a cosmological constant at current precision levels. If dark energy was stronger in the recent past, voids would have expanded faster than Lambda-CDM predicts, potentially growing larger and emptier than standard calculations allow. This is a subtle effect and difficult to measure, but it connects the void problem to one of the most active frontiers in observational cosmology. The fourth avenue is the simplest and perhaps the most unsatisfying. It holds that the Boötes Void and the Eridanus Supervoid are genuine statistical outliers that happen to exist within our observable volume, and that Lambda-CDM is correct as formulated. The universe is enormous. Rare events occur in enormous volumes. We should not be too surprised to find a few extreme structures if we survey enough space. This explanation requires no new physics and no modification to the standard model. Its only cost is the philosophical discomfort of accepting that we observe structures whose probability under the standard model is low. How low is too low is ultimately a judgment call. A 1 in several hundred probability for the Boötes Void is unusual but not absurd. A 1 in several thousand probability for the combined existence of multiple extreme structures starts to strain credulity more seriously. The scientific tools to distinguish among these possibilities are not theoretical, they are observational, and many of them are either already operating or about to begin. ESA's Euclid Space Telescope was launched in 2023 and is currently surveying the sky. As of March 2025, Euclid had observed approximately 2,000 square degrees, roughly 14% of its planned total survey area of 14,000 square degrees. The mission's first quick data release in March 2025 demonstrated its capabilities with the classification of more than 380,000 galaxies and the identification of over 500 gravitational lens candidates. Euclid's first major cosmology data release is planned for October 2026. When complete, the full Euclid survey will map billions of galaxies across 1/3 of the sky, using both visible and near-infrared imaging, providing three-dimensional maps of the cosmic web with unprecedented depth and resolution. These maps will contain thousands of voids at various redshifts, enabling statistical analysis of void sizes, shapes, and density profiles across cosmic time. For the first time, astronomers will be able to construct a comprehensive census of voids in the observable universe and compare their properties directly to Lambda-CDM predictions with the precision needed to detect or rule out the kind of excess. Large void population that structures like Boötes and Eridanus hint at. The Dark Energy Spectroscopic Instrument has been operating since 2021, mapping tens of millions of galaxies with spectroscopic precision from its base at Kitt Peak National Observatory in Arizona. DESI's primary goal is measuring the expansion history of the universe through baryon acoustic oscillations, but its galaxy maps provide extraordinary detail on the cosmic web, including the void population. DESI's first data release already produced some of the most precise BAO measurements ever made. As its survey continues and its volume grows, DESI will contribute increasingly powerful constraints on the distribution of voids and on the properties of dark energy that govern their growth. The Vera C. Rubin Observatory in Chile achieved first light in mid-2025 and is now preparing to begin its primary survey operations. Designed to conduct the legacy survey of space and time, It will image the entire accessible southern sky repeatedly over a 10-year period. Its 8.4-meter mirror and 3.2 gigapixel camera will detect galaxies fainter and more distant than any previous ground-based survey, providing photometric redshifts for billions of objects. This immense dataset will enable the identification of voids at distances and depths previously inaccessible, extending the void census to earlier cosmic epochs and testing whether the extreme structures we observe locally are typical of the universe at large or peculiar to our cosmic neighborhood. Together, these three instruments represent the most powerful suite of cosmological survey tools ever assembled. Within the next several years, they will collectively map the three-dimensional distribution of matter across a substantial fraction of the observable universe, with a level of detail that was unimaginable when Kirshner first discovered the Boötes Void in 1981. The statistical power of these surveys will be transformative. Instead of debating whether one or two extreme voids are consistent with Lambda-CDM, astronomers will be able to measure the entire void size distribution and compare it quantitatively to predictions. If the distribution matches, Lambda-CDM survives this test, and the Boötes Void becomes an acknowledged outlier, interesting but not destabilizing. If the distribution shows a systematic excess of large voids beyond what the model predicts, something fundamental must change, either in the initial conditions, the gravitational physics, or the dark energy model that governs void evolution. There is also the possibility that these surveys will reveal structure within voids that current instruments cannot see. Radio surveys searching for neutral hydrogen emission, infrared surveys detecting low surface brightness galaxies, and weak gravitational lensing analyses mapping dark matter directly could all uncover material within the Boötes Void and other large voids that optical galaxy surveys have missed. If large voids turn out to be less empty than they appear, if they contain significant populations of dark or faint galaxies that bring their density closer to the cosmic mean, the statistical tension with Lambda-CDM would ease. This is a real possibility. Current void galaxy catalogues are almost certainly incomplete. The faintest and most diffuse objects are the hardest to detect, and voids, by definition, contain objects that are sparsely distributed and challenging to observe. Every improvement in survey depth has the potential to revise void density estimates upward. But 4 decades of improving observations have not yet filled in the Boötes Void. They have confirmed it. They have sharpened its boundaries. They have revealed its internal filament and catalogued its sparse galaxy population. But they have not made it go away or reduced it to an ordinary underdensity. The void has resisted every attempt to normalize it. The science is not settled. It is actively evolving, with new data arriving on timescales of months rather than decades. The instruments are in place, the surveys are underway. The statistical frameworks for testing void populations against Lambda-CDM predictions have been developed and refined. What remains is the data itself, the billions of galaxy positions and redshifts that will fill in the map of the cosmic web with enough detail to answer the question definitively. The Boötes Void has been waiting for more than 40 years. The Eridanus Supervoid has been debated for nearly 20. The CMB Cold Spot has remained anomalous through 3 generations of satellite observations. The excess ISW signal from supervoids has been reported, challenged, and reported again across multiple independent datasets. All of these threads converge on the same question. Does the universe produce extreme voids more readily than our best model predicts? The answer will come from observation, not from theory. And the observations are coming. Within the next several years, astronomers will know whether the Boötes Void is a rare but explicable fluctuation within a well-understood cosmos, or an early signal that our understanding of how the universe builds its largest structures is incomplete. Either outcome will advance cosmology. One confirms the model at its most challenging boundary. The other opens a door to physics we have not yet imagined. But before those results arrive, there is one more dimension to this story that deserves exploration. The Boötes Void and structures like it are not just tests of cosmological models. They are not merely statistical data points to be compared against simulations. They are windows into what the universe is, structurally and fundamentally, at its deepest level. They reveal something about the nature of cosmic architecture that goes beyond any single model or any single measurement. What extreme voids tell us about the character of the universe, about the meaning of structure and emptiness, about how we understand our place within this vast and largely hollow cosmos? That is where this story ultimately leads. Step back from the data for a moment. Step back from the redshift surveys and the simulation outputs and the statistical distributions and the acronyms. Step back from Lambda-CDM and the integrated Sachs-Wolf effect and the DES Year 3 analysis and the Euclid mission timeline. Set aside the numbers and the error bars and the sigma values. Step back from all of it and ask the simplest possible version of the question. What does it mean that the universe built a hole this large? The Boötes Void is not terrifying because it is empty. Emptiness is one of the most ordinary features of the cosmos. The vast majority of the observable universe by volume is void. Every direction you look, most of the space between here and the cosmic microwave background contains almost nothing. Voids are not exotic. They are the default state. They are what the universe looks like when gravity has not had enough local advantage to pull matter into dense concentrations. They are the background against which all cosmic structure is painted. In a universe dominated by dark energy, where the expansion of space accelerates in every region not held together by its own gravity, voids are inevitable. They are predicted by the Standard Model, confirmed by every major galaxy survey, and understood through physics that has been tested and validated across multiple independent lines of evidence. There is nothing inherently alarming about empty space. What makes the Boötes Void unsettling is not the emptiness itself. It is the scale of the emptiness. It is the fact that this particular void is so large, so empty, and so coherent that it occupies a region of parameter space where our best model of cosmic structure formation begins to strain. The issue is not that voids exist. The issue is whether this void fits within the range of voids that the universe should be able to produce given the initial conditions we measure and the physics we understand. This distinction matters enormously because it determines what the void is actually telling us. If the Boötes Void is a rare but statistically acceptable fluctuation within Lambda-CDM, it tells us that the universe is capable of producing more dramatic structures than the typical simulation suggests, but that our model remains fundamentally sound. If the Boötes Void is genuinely anomalous, too large or too empty to arise comfortably from the initial conditions and gravitational physics that the Standard Model assumes, it tells us something far more important. It tells us that the process by which the universe builds structure on its largest scales may be more complex, more extreme, or less well understood than we currently believe. Either answer is valuable, neither answer is comfortable. The first possibility, that the void is a tolerable outlier, carries its own unsettling implications. It means the universe is a place where regions 330 million light-years across can be emptied of 97% of their expected galaxy population through perfectly ordinary physics. It means the cosmic web, for all its elegance, produces structures of staggering asymmetry, places where matter concentrates into filaments containing thousands of galaxies per unit volume, right next to places where the same unit volume contains almost nothing at all. The contrast between a rich galaxy cluster and the interior of the Boötes Void is not a subtle gradient. It is a cliff. The difference in galaxy density between a node of the cosmic web and the deep interior of the void spans roughly 3 orders of magnitude. That is a factor of 1,000. The universe, even when operating entirely within the predictions of its most successful model, builds architecture of breathtaking extremity. This tells us something about the nature of gravitational instability that is easy to overlook when the mathematics is presented in textbooks as a clean, orderly process. The mechanism that turns tiny initial density fluctuations into galaxies and voids is not gentle. It is not a smooth, measured redistribution of matter across conveniently defined regions. It is a runaway amplification mechanism that takes differences of 1 part in 100,000 and over 13.8 billion years converts them into differences of 1 part in 1,000. The initial conditions were almost perfectly uniform. The final state is wildly non-uniform. The cosmic web is the most dramatic amplification of initial conditions that we know of anywhere in physics. Quantum fluctuations smaller than a proton became structures spanning hundreds of millions of light-years. The contrast ratio between the densest and emptiest regions of the universe grew by a factor of 10 million over cosmic time, and the Boötes Void is one of the most extreme products of that amplification. It sits at the boundary where the amplification process has had its most dramatic effect on the underdense side of the ledger. The second possibility, that the void is genuinely anomalous, is scientifically more consequential and potentially more exciting. If the standard model cannot comfortably produce the Boötes Void, the Eridanus Supervoid, and the handful of other extreme structures observed in the cosmic web, then something about our understanding of structure formation is incomplete. The candidates for what might be missing have been discussed. Modified initial conditions from inflation, modified gravity on cosmological scales, dynamic dark energy that varies in strength over time or space, enhanced variance in the primordial density field. Each of these candidates would, if confirmed by observation, represent a major advance in fundamental physics. Each would change how we understand the forces and conditions that shape the observable universe from its earliest moments to the present day. But here is what makes the void problem genuinely interesting rather than merely technical. The tension does not come from a failure of observation or a mistake in data analysis. It comes from the structure of the universe itself. The Boötes Void is not an artifact. It is not a measurement error. It is not a systematic bias in a galaxy catalogue. It is a 330 million light-year region of space that has survived over the entire history of modern galaxy surveying using multiple independent methods without diminishing in scale or significance. The tension it creates is real because the void is real. And when a real structure in the real universe strains the predictions of a model, the strain deserves to be taken seriously regardless of whether it ultimately leads to new physics or is resolved within the existing framework. Cosmic voids offer something else that makes them scientifically irreplaceable, something that connects the story of the Boötes Void to the deepest open questions in all of physics. They are the best natural laboratories in the universe for studying dark energy. This claim is not hyperbole. It follows directly from the physics of void interiors. In the dense parts of the cosmic web, gravity competes with dark energy at every scale. Galaxy clusters hold themselves together gravitationally. Filaments resist expansion through the mutual attraction of their constituent matter. Even individual galaxies maintain their structure against the outward push of cosmic expansion. In all of these environments, the effects of dark energy are tangled up with the effects of gravity, making it difficult to isolate and measure dark energy's contribution to cosmic dynamics. In voids, that complication largely disappears. Matter is so sparse that gravity contributes almost nothing to the local dynamics. Dark energy dominates unopposed. The expansion rate within a void is driven almost entirely by dark energy, with negligible gravitational contamination from local matter concentrations. This makes voids the cleanest environments in the universe for measuring how dark energy behaves. If dark energy is a cosmological constant, as the simplest interpretation of Lambda-CDM assumes, then its density is the same everywhere and at all times. It does not vary from one region of space to another. It does not change as the universe ages. It is a fixed property of space-time itself. In this scenario, voids should expand at a rate that is precisely determined by the cosmological constant and the local matter density. The expansion should be uniform in all directions, preserving the roughly spherical shape of the void over time, and the growth rate of the void should follow a specific trajectory that can be calculated from first principles. If dark energy is something other than a cosmological constant, if it varies in strength over time or space, then void behavior would deviate from these predictions in measurable ways. A dark energy field that grew stronger over time would cause voids to expand faster than the constant dark energy prediction. One that weakened would cause slower expansion. Spatial variations in dark energy strength would cause voids to expand asymmetrically, becoming elongated or distorted rather than maintaining spherical symmetry. Measuring the expansion rates, shapes, and growth histories of voids across a range of distances, which corresponds to a range of cosmic epochs since light from more distant voids left those structures earlier in the universe's history, provides a direct probe of dark energy's nature that is complementary to and independent of other methods like supernova distance measurements or baryon acoustic oscillation analysis. Voids offer a window into dark energy that no other cosmic structure can match. The Boötes Void, as one of the largest and nearest well-characterized voids, is a prime candidate for this kind of analysis. Its proximity allows measurements that are impossible for more distant voids. Individual galaxies within and around it can be studied in detail. Their velocities can be measured with high precision, mapping the outflow pattern that reveals how fast the void is expanding. The shape of the void can be determined from three-dimensional galaxy maps, testing whether it has remained spherical or become distorted. These measurements, combined with similar analyses of hundreds or thousands of smaller voids at various distances, will provide one of the most powerful constraints on dark energy available to observational cosmology in the coming decade. The relationship between voids and the cosmological principle deserves careful consideration as well, because it connects the Boötes Void to one of the most fundamental assumptions in all of physics. The cosmological principle, the assumption that the universe is homogeneous and isotropic on sufficiently large scales, is one of the foundational pillars of modern cosmology. It simplifies the mathematics of general relativity enormously, allowing scientists to describe the evolution of the entire universe using a single set of equations. It is the reason we can speak of a single expansion rate, a single average matter density, a single cosmic age. Without it, cosmology becomes far more complicated, requiring different equations for different regions of space and abandoning the concept of universal properties. Extremely large voids test this assumption in a straightforward way. If the universe is truly homogeneous on large scales, then the statistical properties of the matter distribution should be the same everywhere, when averaged over volumes comparable to the homogeneity scale. The existence of a void 330 million light-years across does not by itself violate homogeneity, as long as voids of that size appear with roughly equal frequency in every direction and at every distance. The cosmological principle does not require the universe to be smooth on small scales. It requires smoothness only when you average over large enough volumes. The question is what counts as large enough. If the homogeneity scale is 100 megaparsecs, as some analyses suggest, then a void with a radius of 62 megaparsecs is a structure comparable in size to the smoothing scale itself. That makes the Boötes Void not a violation of homogeneity, but a structure that pushes right up against the boundary where homogeneity is supposed to apply. It occupies the uncomfortable middle ground between structure and smoothness, too small to violate the principle definitively, but too large to be comfortably dismissed as a minor fluctuation. Recent work has explored this boundary from a different angle. Researchers, including Dr. Indranil Banik at the University of Portsmouth, have investigated whether our own location inside a local underdensity, the KBC void, could influence local measurements of the cosmic expansion rate and contribute to the Hubble tension. Their models suggest that a local supervoid with properties consistent with observations could reduce the Hubble tension from approximately 3.8 sigma to roughly 1.1 to 1.3 standard deviations. This work was presented at the National Astronomy Meeting in 2025 and published in monthly notices of the Royal Astronomical Society and Classical and Quantum Gravity. The results remain debated, but they illustrate an important principle. Voids are not passive empty spaces that can be ignored when interpreting cosmological measurements. They are active features of the cosmic landscape that can systematically influence the observations made by anyone living inside them. If the KBC void does contribute to the Hubble tension, it would mean that one of the most significant unsolved problems in modern cosmology is partly an environmental effect, a consequence of our particular location within the cosmic web, rather than a sign of new physics operating at cosmological scales. This possibility challenges the implicit assumption that our measurements reflect universal properties. It suggests that cosmic address matters, that where you are within the web affects what you measure and how you interpret it. This is not a violation of the cosmological principle in the formal sense. The principle states that the universe is homogeneous on large scales, not that every local measurement will match the universal average, but it is a practical complication that makes precision cosmology harder than it would be if we lived in a perfectly average region of space. The Boötes Void contributes to this conversation not through its effect on our own measurements, since we do not live inside it, but through what it reveals about the range of environments the universe produces. If the universe can build a region 330 million light-years across with a 97% galaxy deficit, it can presumably build regions of comparable size with more moderate deficits. The KBC void, with its 20% underdensity spread across a much larger volume, is arguably a less extreme version of the same phenomenon. The existence of the Boötes Void makes the existence of the KBC void more plausible, and by extension makes the void-based explanation for the Hubble tension more difficult to dismiss. There is also the question of what remains genuinely unknown about the Boötes Void itself. Despite 4 decades of study, several important properties of the void are still uncertain. Its exact boundaries, as discussed earlier, are not sharply defined. The density profile of its interior, the precise way matter density increases from the center outward toward the surrounding cosmic web, is not yet measured with the precision available for some smaller, nearer voids. Whether the void is a single monolithic structure or a collection of overlapping smaller voids that merged over cosmic time has not been definitively resolved. The tube-shaped filament running through its interior might be a fossil wall between formerly separate voids, or it might be a genuine filament that happens to thread through an unusually empty region. The populations of galaxies and dark matter halos within the void are almost certainly incompletely catalogued. Faint dwarf galaxies, low surface brightness objects, and dark halos containing no visible galaxies would all be missed by current optical surveys. Future observations across multiple wavelengths will systematically address these uncertainties and fill in the gaps in our current knowledge. Radio surveys detecting neutral hydrogen emission from gas-rich void galaxies will extend the census to objects that are completely invisible in optical light. Infrared observations will reveal low surface brightness galaxies that scatter below the detection thresholds of current surveys. Weak gravitational lensing analyses, in which the shapes of background galaxies are statistically distorted by foreground dark matter, will map the total mass distribution within the void regardless of whether that mass is visible or dark. The combination of these techniques, enabled by Euclid, the Vera Rubin Observatory, and future radio facilities like the Square Kilometre Array, will eventually produce a comprehensive portrait of the Boötes Void that captures not just its galaxy population, but its full matter content, visible and invisible alike. If these measurements reveal that the void contains significantly more matter than current galaxy counts suggest, in the form of dark halos, diffuse gas, or faint galaxies below current detection limits, the statistical tension with Lambda-CDM would be reduced. The void would still be large and underdense, but perhaps not as extreme as its galaxy deficit implies. On the other hand, if multi-wavelength observations confirm that the void is genuinely as empty as it appears, the tension will sharpen. The void will become a harder problem for the standard model, one that cannot be resolved by appealing to incomplete observations. Either outcome teaches us something. Either outcome advances our understanding. This is the nature of science at the frontier. The value of a structure like the Boötes Void is not that it provides a definitive answer to any single question. It is that it creates the conditions under which definitive answers become possible. The void defines the test. It establishes the stakes. It sets the terms of the confrontation between theory and observation. It forces the model to make predictions in the regime where predictions are hardest and where failure would be most informative. The void is a crucible for cosmological theory precisely because it sits at the edge of what theory can comfortably explain. There is something deeper here as well, something that transcends the technical details of any particular model or measurement. The Boötes Void forces us to confront a truth about the universe that is easy to forget when we focus on the bright, active, matter-rich regions where most astronomical research takes place. The universe is not primarily a collection of objects. It is primarily a collection of spaces. Galaxies, stars, planets, clusters, filaments, all of the structures that dominate our observations and fill our textbooks and inspire our imaginations, all of them together occupy a minority of the cosmic volume. The majority of the universe is void. The majority of the universe is silence. The majority of the universe is the absence of the things we find most interesting, most familiar, and most meaningful. When we picture the cosmos, we instinctively picture the bright parts, the galaxies and nebulae and star fields. But those bright parts are the exception. The void is the rule. We have built our entire understanding of the universe by studying the small fraction of it that contains enough matter to glow. This is not a deficiency of the cosmos. It is not a failure of the universe to fill itself with structure. It is the natural, expected, physically necessary outcome of how gravity and dark energy interact over cosmic time. Structure formation is inherently asymmetric. Gravity pulls matter together into ever denser concentrations, but it does not create matter to fill the spaces left behind. The voids are the price the universe pays for building galaxies. Every filament that forms drains matter from the surrounding volume. Every cluster that collapses deepens the void around it. The cosmic web is a zero-sum architecture. The bright parts exist because the dark parts gave up their matter. The fullness of the clusters is funded by the emptiness of the voids. The Boötes Void is the most extreme confirmed expression of this principle that we have identified in the observable universe. It is a region where the process of matter drainage proceeded further, faster, and more completely than almost anywhere else we have looked. Whether it achieved this through ordinary physics operating at the extreme tail of its probability distribution, or through some additional mechanism not yet captured by the standard model, the result is the same. 330 million light-years of nearly perfect emptiness, containing the ghostly remnants of a cosmic web that once threaded through it but has now almost entirely dissolved, surrounded by walls and filaments that grew rich partly by consuming what the void lost. And there is one final consideration that the Boötes Void raises, one that connects to the very nature of scientific understanding itself. The void was discovered in 1981. It has been studied continuously for more than 4 decades. In that time, our cosmological models have been refined, our telescopes have improved by orders of magnitude, our simulations have grown from primitive sketches to sophisticated reproductions of cosmic evolution, and our understanding of the forces governing the universe has deepened enormously. And yet, after all of that progress, after all of those improvements in every dimension of observational and theoretical capability, the Boötes Void remains a structure that does not fit entirely, comfortably within our best theoretical framework. It is not unexplained. It is not mysterious in the sense of being beyond physical comprehension. But it is unsettled. Its status within the standard model remains a matter of active scientific debate rather than settled consensus. This is not a failure of cosmology. It is cosmology working exactly as it should. The purpose of a scientific model is not merely to explain what is already known. It is to make predictions that can be tested against new observations, and to be challenged precisely at the boundaries where its predictions become uncertain. The Boötes Void is one of those boundaries. It is a place in the universe, and a place in the landscape of scientific knowledge, where the standard model is being tested at its limits. The test is not yet complete. The data that will complete it are being collected right now by instruments orbiting the Earth and observatories scanning the sky from mountaintops and deserts. Within the next several years, those data will provide the statistical power to determine whether the void is a rare but natural product of standard physics or a signal pointing towards something we have not yet understood. Until that determination is made, the Boötes Void stands as a monument to both the achievements and the limitations of modern cosmology. It is a structure that we can describe, measure, map, and model with extraordinary precision. It is also a structure that we cannot yet fully explain, and in science, the gap between description and explanation is where the most important discoveries live. The void so large it should not exist. The phrase deserves one final clarification. It does not mean impossible. It has never meant impossible. It means unexpectedly large under standard assumptions. It means difficult to reconcile cleanly with the predictions of our most successful model. It means scientifically controversial and tension-producing in ways that force us to take the emptiness seriously as a source of information about the universe. The Boötes Void does not break physics. It does not collapse cosmology. It does not prove the multiverse or signal the intervention of forces beyond our understanding. What it does is something quieter and, in the long run, more important. It reminds us that the universe is not obligated to be convenient. It is not required to produce structures that fit neatly within the central predictions of our models. It is allowed to be extreme. It is allowed to be surprising. It is allowed to build regions of space so vast and so empty that they push against the boundaries of what we thought was possible, forcing us to look more carefully, measure more precisely, and think more deeply about how the cosmos assembled itself from almost nothing into the intricate, beautiful, and profoundly uneven architecture we observe today. The terrifying part of the Boötes Void is not that it contains almost nothing, it is that its nothingness may be telling us something. Something about the initial conditions of the universe, or the behavior of gravity on the largest scales, or the nature of the dark energy that drives cosmic expansion, or the limits of how well we understand the growth of structure across 13.8 billion years of cosmic history. The void does not shout, it does not flash or pulse or radiate. It communicates through absence, through the galaxies that are not there, through the matter that drained away, through the silence that fills 330 million light-years of space. And in that silence, if we listen carefully enough, there may be a message, not a supernatural message, not a mysterious signal from beyond known physics, a scientific message. A message encoded in the size and depth and shape and population of the largest confirmed emptiness in the observable universe. A message that tells us whether our model of reality is as complete as we believe, or whether the universe has been quietly building evidence, in the form of an impossible void in the constellation Boötes, that something fundamental about how structure grows across cosmic time remains to be discovered. We are listening. The instruments are pointed at the sky, the surveys are mapping the web, the simulations are running, and the Boötes Void, patient and silent and incomprehensibly vast, waits for us to finally understand what it has been trying to say for more than 4 decades. The answer is coming, and when it arrives, it will be written not in light but in darkness.